My name is Harald Ebeling. I'm faculty at the Institute for Astronomy at the University of Hawaii. And so this is IFA Ihilo here. We have a campus in Manoa here across all islands. And my specialty are galaxy clusters, which I use to study dark matter, galaxy evolution, the evolution of structure in the universe, and a little cosmology too. So I look at everything from the nearby universe, which means a few megaparsecs out, to the very edge of the universe, redshift 4, 5, 6, to as far out to the Big Bang as we can go. A lot of my work is in finding galaxy clusters. So I'm a bit of a science facilitator, you might say. Well, I try to do actually the hardcore science too, but I also like to provide a service to the community. I find galaxy clusters that other people can observe, and which is kind of what JWST did. So I found that galaxy cluster, and 20 years later, somebody else selected it for JWST to observe. So, and in that capacity of just finding new targets for people to look at, I'm doing a lot of work on Maunakea here in Hawaii. And so I have an observing run coming up. I have a long-standing project with HST, the Hubble Space Telescope, where we take snapshots of galaxy clusters that I have selected based on their X-ray emission, which I suspect to be very massive, which I suspect to be powerful gravitational telescopes, just like the one that JWST just observed. But we need to confirm them first. We can't just point JWST at each candidate. That would be a little expensive. So I used the telescopes on Maunakea to get redshift of these objects first, to get ground-based images, to confirm that they are really as exciting and as massive as we expect them to be. So I use both the Hubble Space Telescope snapshots, very, very short images, and follow-up observations from Maunakea to select the very best objects for really deep and detailed studies. So yeah, so we're excited to see that one of the first images that JWST took was actually one of my galaxy clusters, except nobody knows that it's my cluster. So I discovered that thing 20 years ago, but I don't think we ever published that. That's why I probably never get credit for it. But it was exciting to see it on the big screen. And when I saw the image that was released on Tuesday, that was one of those Pixar moments. When you, so I saw that image, and it doesn't look real. When you see one of these animated movies and you think, wow, they did a really good job, that looks totally real. And you kind of think this must be a simulation. This can't be right. It's just too perfect. And you want to zoom in, and at some point you'll see the pixelation, and it's going to become grainy. But you zoom in, and it's still perfect. Colors, resolution, you see all this detail. So it was absolutely amazing. And I should say that's as a professional astronomer. Yeah, so we've seen a lot of those data, but it really blew even us away. How the depth and the clarity and the detail that we saw. And now to get a little bit to the science, because it's not just pretty images, we wrote a paper on those data within 4 days of them being released. And so we actually tried to extract as much science as we could in a few days. And it is astounding how much you could get directly out of those data without doing any follow-up, without digging into anything else. JWST gets you the colors in a huge range of filters. It gives you spectroscopy. We got redshifts directly of objects at redshift 5 or something out of the same data from the slitless spectroscopy. It's a deep image, but this is not the best that JWST is going to do. This was a press release. It's the first thing. It's the first glimpse of what that telescope is able to do, and it was a stunning display of the power of that new facility. So we're very excited about seeing really the first galaxies form. This is what this is about. So to explain a little why galaxy clusters are exciting to me, or that specific aspect of galaxy clusters, what was observed here was a gravitational lens. So this is a galaxy cluster which is very massive, so something that I like and select specifically, which means it has a lot of dark matter in it. It's very massive, and it acts like a telescope itself. It bends light through the force of gravity, and it magnifies everything that's behind it. So effectively, we have a telescope, JWST, looking at another telescope, namely a natural telescope, which is the cluster. So we're getting double magnifying power. And we're utilizing that to magnify galaxies that are so faint that there's no way we could see them in any other way. So we're looking to higher redshift, to fainter magnitudes. We're seeing objects at redshift 6, 7, 8, the very faintest galaxies, the very first generation of galaxies that formed in the universe. And that is one of the key science goals of JWST, to reveal that first generation of galaxies, the very beginning of structure formation in the universe. And I can't say that, you know, that very first image gave us all the answers, certainly not, but it demonstrated very, very nicely what will be possible in the years to come. So we're very excited. We are able to see farther and fainter than we're able to do before. And we knew this was coming. So this is not something we see the image, oh, total surprise. This is what JWST was designed to do. So the satisfaction is more that it delivers. This is exactly what we hoped it would do, and it does. And the other aspect which I should mention is, and again, this is why galaxy clusters are so exciting to me, there is a dual effect. We're not just using the galaxy cluster to magnify distant objects and probe that very distant universe all the way back to the Big Bang. We are doing the inverse too. We're using those multiple images that we see of these faint galaxies to learn something about the foreground cluster, the lens itself. And that is very exciting because we can now make a model of that lens. If we have enough of these lensed images scattered all across that field, then we can model the dark matter that does the distortion of all these distant galaxies. And we can recreate the dark matter field in that galaxy cluster. And you know, as the name suggests, dark matter is invisible. There's no other way to figure out where that dark matter is. Is it clumpy? How far does it extend? What is the concentration of dark matter relative to the galaxies? These are all questions that we can answer now, thanks to JWST and thanks to gravitational lensing. There are two aspects. One is the relatively nearby universe, where I think we will learn a lot about star formation in galaxies, about the evolution of galaxies through mergers. There was another, one of these first images was Stephan's quintet, which is a collision of galaxies. I think that is going to be extremely exciting to see galaxy evolution happen, to see star formation, look through the dust clouds at low redshift and see the dynamics of galaxy formation. The other part is going to be that super distant universe. And I expect JWST to, at some point, go much deeper than what it did just last week. So there will probably be an ultra deep field, which is going to blow us all away, which is going to show so much detail to even higher redshift, to even fainter magnitudes. And what we're going to see, I don't know, because nobody has ever seen that. Which is, of course, the excitement of observational astronomy. With each of these images, we see something that no human eye has seen before.